Hello. First of all, I should introduce myself to you. My name is Ahmed Med, and I am a public relations member at Robust team. I am here to explain the CDR of our rover to you. And now, let's start with the mechanical design. According to obstacles, rocks dimensions and field ground type, we designed our rocker buggy suspension system with 6 wheels. Our own wheels supported with needed specifications. It is 20 cm diameter and 15 cm width to prevent sinking sands. It is also made from PVC, which is light, strong and flexible. It is also connected to the center by a spiral connection to work as a damper for vibration. It is also covered by rubber, as we noticed that many rovers are slipping on smooth rocks. All of these features enable us to finish long distance tasks in a specified time. A rocker buggy suspension system with 6 self-powered wheels and differential gear is used to guarantee a permanent touch to the ground to avoid any tipping or slipping. Additionally, the corner wheels have high torque steering servo motors that enable the robot to rotate around its center smoothly. As we see, our modification in rocker buggy suspension was designed to decrease the distance between the centroid of the robot and the ground by using a geared motor so that it will avoid any tipping in steep cliffs. For more efficient vision system, our rover has 2 cameras. The first one is fixed and it is also an emergency camera. The second camera is a main rover eye and it is fixed on 2 servo motor holders, which gives the camera 2-angle motion. Robust rover chassis is made from 3mm aluminum that could be surface on it. It has boxes for payloads such as circuits, batteries, and onboard lamp. The rover manipulator has 5 degrees of freedom, and instead of designing motors in each joint which consume a lot of motor torque due to their weight, we designed the motors to be placed in the manipulator base. These motors move all joints by using a belt transmission with the appropriate gear ratio. We also designed multitasking in the effector, which includes driller, suction tube, and grip. That enables us to complete the required tasks easily. As shown, the rover's onboard lab mechanism is designed to keep and analyze more than 1 sample at the same time. The sample tubes are fixed on a plate that rotates under the sensor plate that moves down to begin analysis. And now, let's go to the software. Our control system consists of 2 microprocessors on the rover, BeagleBone Black and Raspberry Pi. Also, we got in the control station, pilot and co-pilot. They work together as a distributed system. As we see, the connection between all systems components in normal state, BeagleBone Black is the main controller on the rover, which is mainly responsible for controlling the following subsystems: motion system, navigation system, manipulator, and onboard lamp. And it is connected to a backup camera for emergency states. Raspberry Pi main responsibility is controlling the manipulator camera and the main rover's camera and sends the streaming video over the network. In our system, we cared about handling many failures which could happen to the system. These failures are communication failure between the station and the BeagleBone processor. In this case, the pilot will switch the motion control and navigation system to Raspberry Pi to enable the pilot controlling the rover until the BeagleBone back to work again. Also, in communication failure between the station and the Raspberry Pi to prevent the blindness of the rover, we connected an emergency camera to the BeagleBone, as we see, which is switched on by the pilot in case of Raspberry Pi failure. Also, in communication failure between the station and the 2 microprocessors, in this case, the autonomous mode will start automatically by the BeagleBone or Raspberry Pi and back with the rover to the last location before communication losses.